This is MSJ Chem. In this video, I'll be looking at the Arrhenius equation. The Arrhenius equation uses the temperature dependence of the rate constant K to determine the activation energy. Here we have the Arrhenius equation, which can be found in the data booklet. K is the rate constant, A is the Arrhenius constant, which is also called the frequency factor, EA is the activation energy, and R is the universal gas constant. We also have T, which is the temperature in Kelvin, and E, which is the base of the natural log. The Arrhenius constant A, which is also called the frequency factor or pre-exponential factor, takes into account the frequency of collisions with the correct orientation for the reaction to occur. The Arrhenius equation is often expressed in its logarithmic form, which you can see here. This is the form of the equation for a straight line y equals mx plus c. So a graph of ln k against 1 over t will give a straight line with a gradient negative EA over r. So here we have a graph of ln k on the y-axis against 1 over t on the x-axis. As you can see, this gives a straight line with the intercept lna on the y-axis and a gradient of negative EA divided by r. So the activation energy in joules per mole is equal to the gradient of the line, which has the unit K, multiplied by the universal gas constant. Next we look at an example. Here we have a graph of ln k on the y-axis against 1 over t on the x-axis. From this graph, we'll calculate the activation energy for a reaction. So we'll start by finding the gradient of the line, which is the change in the y-axis divided by the change in the x-axis. The change in the y-axis is negative 5.5, and the change in the x-axis is 0.196 times 10 to the negative 3. This gives us a gradient of negative 30,000. So the gradient of the line is equal to negative EA divided by R. The gradient is negative 30,000, and that's equal to negative EA over R. If we rearrange the equation, we get EA, activation energy, is equal to 30,000 times the universal gas constant, which is 8.31. That gives us the activation energy in joules per mole. If we divide this answer by 1,000, we get an activation energy of 249 kilojoules per mole. The activation energy can also be calculated from values of the rate constant K at two different temperatures. So we can use this equation here, which can be found in the data booklet, to calculate the activation energy.